So our next speaker in this session is Kevin Dalton, and Kevin has completed his PhD at Stanford University before moving on to Harvard, where he is at his current position. And in this talk, he's going to tell us about state-of-the-art methods for scaling and merging. So please take it away, Kevin.
Okay, how's that for microphone placement? Good, thank you. Yeah, so I'm Kevin Dalton. I'm in the Hextra lab right now at Harvard, and I am one of the co-authors of Reciprocal Spaceship. Just do a little plug for starters. It's basically pandas for X-ray crystallography data, if you're familiar with that for machine learning and Python data processing. And I also occasionally contribute to dials. And what I've been tasked to talk about today is an educational introduction to scaling, and then a little bit of information about an algorithm that solves the scaling problem that I've developed over the course of the last 2-3 years now. So in an X-ray diffraction experiment, as Graham showed us earlier, your primary data are these diffraction images that have puncta in them. Those are your Bragg peaks. And very early in data processing, what you do is attempt to predict all the theoretical locations where you might observe a Bragg peak and go and visit all of those locations and try to estimate the photon flux into each of those regions. And that process is called integration. That gives you a set of tabular data, which includes intensities and uncertainties, right? And in addition to that, we also get a bunch of metadata sort of for free, which are just facts about each of the reflection observations, like where they were on the detector or what resolution they're at, and items like that. So in an ideal world, at this point in time, we just, oh, I guess I can use this pointer. Yeah. In an ideal world, at this point, we'd just be able to average all of the redundant observations, get merged intensities, take the square root to get structure factor amplitudes, and then go about phasing and model building. But for various reasons, this doesn't actually work in practice, unless perhaps you have a spherical crystal, which I recently learned is a thing that's possible with laser milling, which is really interesting. The reason this doesn't work sort of out of the box is because diffraction data are sort of badly contaminated with systematic errors, and these vary throughout the data acquisition process. So this is just an example of a very high quality single crystal experiment that we conducted in the lab. And you can see that the average intensity is sort of wandering all over the place throughout the course of crystal rotation. And it's also correlated in this complicated nonlinear way with these other metadata for reflection observation. So this needs to be corrected before you can go ahead and estimate structure factors. And the way we do that is a process called scaling. And that's an iterative algorithm that alternates between two phases, where you first merge, do an initial merge and get intensity estimates that represent the full data set. And then you fit a function that tries to make your observations look more like these merged values. So you correct intensities, merge intensities, feed the new intensities back into the scaling procedure, and iterate until convergence. And once you've done that, you can then convert to structure factors, usually not using a simple square root, but a Bayesian protocol, and then go about your phasing business, whether it be experimental or molecular replacement. And of course, your iterative model building process. And the good news is that this scaling step really works fantastically well, right? It's this technology that's allowed us to put close to 10,000 new structures into the PDB year on year for the last decade. But it's kind of, from a software development standpoint, it's a little bit of a wasteful thing because not all experimental modalities are the same, and we're starting to see more and more exotic types of experiments pop up as time goes on, as sources get brighter, and as we get new sample handling technologies coming online. So in this sort of space of possible experiments, you can think of a conventional rotation method experiment living down here, whereas serial methods would live over here, where you're getting, rather than a bunch of images per crystal, you're just getting a single one typically, and you're not doing rotation method. Laua crystallography, where you have a polychromatic source, would live up there. And you can combine these concepts, right, of serial and Laua and end up with serial pink beam crystallography. Furthermore, you can do something that we did in the Hextra lab, which I really wouldn't recommend, but you can do it nonetheless. You can take your single crystal, large single crystal of the XFEL and collect data that way as well. And all of these experiments sort of pose their own unique challenges to scaling algorithms. So if you think about Laua data, the spectrum that you're dealing with is not flat, right? It is peaked and it has a long tail, and your spots are expressed at different wavelengths. And so they need to be sort of normalized for their corresponding wavelength. And if you are doing a stills method, usually a serial method, you don't get the benefit of integrating over the Bragg spot by rotation, right? So you just get some ill-defined slice through the scattering volume of the Bragg peak. Further complicating things, if you do your experiment at a free electron laser, you're going to end up with large variations shot to shot in the source intensity. So this is the aforementioned single crystal free electron laser data from our group. And the fluctuations here are not because we have different crystals in the beam. It's just, that's the intrinsic variability shot to shot in the brightness of the source. So yeah, and further complicating things in serial, you will end up with different samples having non-isomorphism issues, right? Different cell constants and different mosaic properties. So the solution by and large has been to have separate scaling algorithms for each of these use cases. So if you're doing conventional, you might be using XDS or aimless or Dallas.scale. Serial and Laua, you might be using some of these more unusual software packages, but I'm sure there are users for all of these here. They pretty much do one thing in common in all cases, which is estimate some either per image scale or smooth image scale, as well as temperature factors that vary throughout the data acquisition. But they kind of have these bespoke algorithms built into them to deal with their particular use cases. So something that I really believe is that we won't be able to predict where users are going to take us next in this space of possible experiments. So what I've been really interested in is trying to design algorithms that are, scaling algorithms in particular, that are robust to being anywhere in this kind of space. And what I'll describe next is my kind of first attempt at this, which is an algorithm that replaces this sort of central slab in the processing pipeline that I showed at the beginning. So it takes in integrated data and it outputs structure factors. So how do we do it? It's actually pretty intuitive. It starts with sort of two assertions that if we're going about this process of trying to find the correct set of structure factors, we'll know when we get there if they satisfy two criteria, right? That they're consistent with the data that we observed. And in addition to that, that they're consistent with our expectations from first principles about how structure factors ought to be distributed. So these are the Wilson distributions that, that Graham introduced earlier. It turns out that using this machinery called variational inference from the statistics literature. You can recover models like this, sets of structure factors and error estimates that satisfy these criteria by maximizing this very simple formula. It's really just two terms, and the first one encourages the solution to follow the first criterion, and the second term encourages the structure factors to stay pretty close to our prior distribution. And how exactly you choose to parameterize this sort of model is a modeling choice, and there are many, many ways you can imagine doing it. As a first pass, what I'm describing in the following slides uses a truncated normal distribution to represent structure factors, and it uses those Wilson's priors that came from the random atom model. And in addition to that, it has some scale factor parameters which are normally distributed, and you have your pick of a normal or t-distributed error model in our implementation. And we're just going to use gradient-based optimization in TensorFlow to maximize this elbow objective function with respect to our structure factors and recover our estimates. Okay, and this is kind of how the model looks graphically. This is a typical way that statisticians visualize these sorts of models, and it just says that the intensities you observe should be calculable from the structure factors and this local random variable that I'm going to call scale. And the particular arithmetic relationship that links them is really simple. It's just that the intensity should be the square of the structure factors modified by some multiplicative systematic error term. But I haven't really told you what is scale or how we're going to learn that yet. And it's a little bit of a ephemeral thing, but I did allude to this earlier. It should depend on the context that a particular reflection observation is in. So it should in some way depend on all of these things that we showed in the beginning, you know, the crystal rotation, the polarization angle, scattering angle, facts about the reflection. So scale should in some way be calculable from the per reflection metadata. But I don't know how to write it down mathematically in the general case. So what we need to put in here is some kind of function that we can learn that will give us a way to jointly optimize our structure factors with a model that ingests metadata and outputs our scale estimates. And the simplest one I can think of is this sort of baby's first neural network, which is called a multi-layer perceptron. It's the most simple deep neural network, and this simple model turns out to work pretty well. So to flip back, what we're going to actually learn in this case are the parameters of this neural network and the structure factors. We're going to optimize them jointly by maximizing that elbow function. And that gives us a pathway to go, as I mentioned before, from integrated data directly to structure factors without, the scaling is kind of implicit in this model fitting. And then I made this claim that this was a sort of general or generic model for scaling, and the reason that's true is because neural networks, is a well-known result, are universal function approximators. So in principle, this thing can learn any sort of correction that might be, germane to your particular application use case. So in this scenario, what we have is we no longer have to change the model. We don't have to build a special model for partiality and a special model for wavelength normalization. We can just change the metadata that we supply into the scale function. And this is work that just came out in Nature Communications, and if you're interested in it, I suggest you take a look. There's a lot more detail in the paper about how exactly you do this. I've been a little bit high level in terms of the math. But we applied it to 3 use cases in that paper, and the first of which was just conventional rotation method data. This was a room temperature sulfur SAD data set of lysozyme. And I'm just showing here the experimental density modified difference map. And it performs pretty well. And I think the map quality is pretty high. I'm not willing to make any claims that it outperforms any other piece of software, but it's, you know, at least it performs adequately on this task. And to accomplish this as metadata, I just supplied pretty much everything that came in the dials MTZ file. So that includes like the resolution of the reflections, the P1 Miller indices, the detector positions, background estimates, and polarization factors. And then a second example, using the same code base, we showed that you could actually apply it to not just LAWA data, but even time-resolved LAWA data. So this is photoactive yellow protein. It undergoes this trans to cis isomerization when it's hit by blue light. And this is our time-resolved difference map where we see, you know, features consistent with the excited state at this 2 millisecond time point. And to do wavelength normalization in this context, all we had to do was provide the empirically determined spot wavelengths as metadata. And then the final example is a serial femtosecond crystallography data set that was processed by Aaron here. And this is a zinc metalloprotease, and you can see in this anomalous difference density here that you get strong anomalous signal for the zinc ion here in the active site. This is contoured at 5 sigma, I believe. And the way that we encode this kind of post-refinement of partiality task is by taking our empirically observed Ewald F-sets, which are just the distance between the Bragg peak and the Ewald sphere, and providing that as metadata. And there's just some peak heights here if you're interested. The interesting thing here is that it really performs very terribly without this Ewald offset metadatum. Yeah, so this is where we're at right now. This is somewhere between a research project and a technology at this point. It's definitely something that people can download and use if they're savvy and like to tinker with things. And also these images were generated by OpenAI's text-to-image model, which is also somewhere between a research project and a technology, but I think it's much closer to a technology, although it doesn't do so well with human language yet. And yeah, with that, I'll just acknowledge the lab. And we have a bunch of collaborators. You know, Wukitsa, Biocars, Igor at AnyCat, Aaron and Derek and Nick from LBNL. I'm funded by the Burroughs Wellcome Fund at the moment. And with that, I'll take any questions. And if you want to play with it, the package is called Careless. You can install it by pip.
Thank you very much, Kevin. It's a fascinating talk. I can already see a hand raised with a question further back up the hall.
Hi, Kevin. Thanks. So it sounds like a very elegant approach. There's one thing that I worry about, though. So I'm very frustrated when I come across entries in the protein data bank where people have applied the French Wilson correction to get the posterior probability of data. And one of the reasons I find it frustrating is because the French Wilson requires you, like your method, to have a prior probability distribution, and you force things to agree better with that. And the problem is that unless you take everything into account, your prior probability distribution can be wrong. So if you have anisotropic data, or if you have translational non-crystallographic symmetry, or if you have any one of a number of pathologies, your algorithms are going to go wrong, or it's going to somehow force things more into not having those features of the data. And I was wondering if you've worried about that and if you have any thoughts about it.
I would say my thoughts about this are mostly that I would love anyone to come help me with diagnostic tools for this package. We do accept pull requests. But yeah, I totally agree with you. That's why I say it's really not a technology yet. It's not there as something that a routine user can download and be confident in the analysis. You want to have a well-characterized system in most cases. And for our use case, it made sense to build it because we're mostly targeting time resolved. And in that case, we usually have very high quality reference data and really nice crystals. But yeah, in the general case, if you have to deal with things like twinning, I don't have the answer for it yet. I think they can be built into the model longer term. You would just have to figure out a way to, like, in the case of twinning, you could imagine jointly learning the twin fraction and having a prior on that.
And probably you would want to keep the data before any of this correction, and then as you learn more by solving the structure, then go back.
Yeah, totally.
There's some questions on Slack. So can the scaling algorithm be also used to scale anomalous data sets?
To scale anomalous?
If the scaling algorithm can be used to scale anomalous data sets.
Oh yeah, absolutely. That's the thermolysin example is anomalous, and the lysozyme example is anomalous too.
And there's one more question on Slack from David McDonough. Is the neural network architecture the same for each application? And if so, how was it optimized?
For 2 of 3, it's the same. In the case of the serial data set, we added some per image terms. Just because you need to be able to learn corrections on a per crystal basis in that case.
Hello, Jean Bricon. This is a very interesting development in just the context of rotation crystallography. I think you've done something that's intermediate between what X-scale does to take into account the context in which each reflection occurs. So these regions on the detector and then slices of image numbers, etc. But they are completely sort of free to float. And something can go wrong if in some of those boxes there aren't enough reflections to do something sensible. Or and there is no interpolation between them. It's all really quite rough in a sense, but very quick. Aimless has a parametrization. So extrapolation and smoothing are sort of built in, but it's much too rigid. So what you see to have done through your neural network is some kind of, I don't know, principal component analysis of the X-scale parameters, or allowing some more local variation to the parameters that are used in aimless. But that's purely for rotation crystallography. What you've been able to do for the other types of data is really interesting.
Yeah, I think it's a promising start. I think that we're going to learn a lot more in the next probably 2 or 3 years about how we can apply this method. Interesting point though about X-scale. I hadn't appreciated that that's how it worked. It'd be probably worth a look to go in and compare our scale factors between this algorithm and those, which is something I really haven't had the time to do.
Very nice work.
Thank you.
We'll follow up.